Yeah, well, thank you for inviting to give a talk here. So, well, I'm not so sure if I will have a lot of probability here, but I will definitely have some integrability and algebraic combinatorics. So, yeah, as you can see from the title, basically I have two parts of this talk. So, basically what I'm going to talk about is I'm going to talk about a certain family of symmetric functions which I construct using q-Hahn integrable models. Namely, it will be just some generalization of models which are usually referred to as q-Hahn TASEP or q-Hahn boson models and stuff like that. So yeah, probably I suppose majority of people, at least non-trivial part of the audience, know something about q-Hahn integrable models and stuff like that. But probably the first part of this title, namely interpolation symmetric functions, might be less familiar to the audience. So let me start with talking in general what is this problem about this interpolation of symmetric functions. So here is the plan. First I will talk about the general background of all these interpolation problems. Then I will talk about q-Hahn vertex models, and then finally I will spend some time explaining the proofs and the methods we use to get all the results. So, well, first of all, let's talk about interpolation problems, and let's start with a very simple toy example as a warm-up. So remember this basic fact that if you have a polynomial in one variable of degree n, then it is uniquely determined by its value at n plus 1 different points. So for our purposes, the important example of the situation will be the following case. So let's define this modified powers, like shifted powers of x, where c are some parameters, which I will assume to be distinct numbers, but it doesn't really matter as long as they are algebraic independent. Well, as long as they are distinct elements of some field of characteristic 0, it will all work. So, and then for these polynomials, what we have is that these polynomials are uniquely determined by the following properties. So first of all, these are polynomials of degree not greater than n. Then these polynomials vanish at all the points c, k, where k is less than n. And finally, they are normalized by some constant, by their value at the point cn. So we have this simple family of polynomials, and well, existence of this family, like in general, existence of this polynomials of degree n is not a surprising fact. It's just a fact of a certain system of n plus 1 linear equations having a unique solution in n plus 1 variables. To be more precise, it's just Mondrian determinant being non-degenerate. So it's a very simple elementary computation. So okay, so now what I want to do, I want to consider this very similar problem, but now I want to consider several number of variables. And moreover, I want to think not about any polynomials, but about symmetric polynomials to make problem well, it will not be simpler, but more beautiful from a certain point of view. So let's talk about the first step here. So let's introduce factorial Schur functions. So namely, factorial Schur functions are determined by this expression. So they, as usual Schur functions, they depend on some partition of length not greater than the number of variables. And then I modify them by adding, again, this parameter c, which I again assume to be some different numbers. And this definition, so I'm giving it as a ratio of two determinants. So if you know the definition of Schur functions as the ratio of two determinants, this is a very similar thing. But instead of taking powers of x, I'm taking this modified powers of x, which are shifted by this number c. So these are so-called factorial Schur functions. So it's easy to see from this formula that, well, these shifted powers of x is just x to some power plus lower order terms. So from this expression, it's not so hard to see that this ratio of two determinants will actually be just Schur function, and some lower terms with respect to the natural grading of the ring of symmetric polynomials. And an important property which we care about when talking about this interpolation business is the following interpolation property. So it turns out that these factorial Schur functions can be determined uniquely as symmetric polynomials with the following properties. So first of all, their degree is less than the number of boxes in the corresponding partition. Then it turns out that these factorial Schur functions vanish at all points xc mu, where xc mu is just determined by this expression. I'm taking my partition mu, make it into a strict partition by adding a staircase, and then I'm looking at the number c corresponding to the parts of the strict partition. So if I will evaluate my factorial Schur function at this point, it turns out that they will all these expressions vanish for partitions mu not greater than lambda and not equal to lambda. And then, well, again, it is normalized by some non-zero constant at the point corresponding to lambda.
So going previous slide and this slide, you're intentionally weakening the triangularity property. You're not using this, like there's a partial order here on partitions which would make the triangularity stronger.
No, so I don't want this because basically what I want, so as you can see under this definition, what I want, I basically again want some system of linear equations when again I have the same number of equations as the number of coefficients. And well, for a polynomial of in n variables of degree not greater than lambda, or not greater than n, the amount of coefficients is exactly the number of partitions of which live in the corresponding, well, they don't have length greater than n and which have not more than n boxes. Well, m boxes where m is the degree of my function. So yes, it turns out that these factorial Schur functions can be determined by this set of properties. And yes, again, similar to the previous case of one variable, this is also not too surprising case because it's, again, will reduce to basically proving that a certain system of linear equations with the same number of equations and variables have a non-degenerate solution. And well, in particular, this statement, as a practical application of this whole story, one can deduce that symmetric polynomials are uniquely determined by their values at this type of points. So okay, so this interpolation property for factorial Schur functions. But it turns out, so as it was mentioned in this question, I have this property where I'm looking at all partitions which are whose number of boxes is less or equal than lambda. So it turns out that I can actually strengthen this property a little bit, or not even a little bit. So it turns out that if I will try to relate the value of factorial Schur functions at points x mu for some different partitions mu, I will actually see some magic happening. So it turns out that this vanishing property is actually way more general than just the fact that it vanishes for this for this particular system of linear equations. It turns out that these factorial Schur functions will vanish for all points x mu which do not contain my partition lambda. So it turns out that actually this solution for these linear equations which I have found for interpolation problem, this solution actually, for some reason, turns out to be a solution of infinitely many other linear equations, which, if you will recall how these points x mu are defined, these points x mu might depend on this number Cn for very large n and so on and so forth. So it turns out that a lot of cancellation is happening here, and actually for all these values of points x mu, these functions will vanish unless this condition holds. And this is already a certain very magical and very highly restrictive property about this set of points x mu where I'm trying to look at this interpolation problem. And one question you might ask yourself is, okay, so I have looked at this situation of factorial Schur functions. Now, what if I want to find some other situations like this? What if I want to look for all the possible choices of points x mu in some n-dimensional space, such that if I will look at the interpolation problem for symmetric functions on these points, then I will be able to find this unique solution which will again satisfy these two properties that their degrees will be, well, these functions will basically respect the natural filtration of symmetric polynomials, and also they will satisfy this vanishing property which basically tells that these functions will vanish at this infinitely many different points determined by this condition that lambda is inside mu. So this is the problem of this interpolation symmetric functions, and this is not like a very recent story. It's actually already like almost 25 years old. So it was observed and studied somewhere in the 90s by several people. So probably most notable names here are Sahi, Knop, Okounkov, and Dershansky, who were doing all the works related to such problems. And yeah, basically, the main idea behind this activity is try to find various sets of points x mu, which will give me this nice vanishing properties. So okay, so this is one solution. So, well, let me give you another solution, which is a pretty significant step above the previous one. So it turns out that there is a different solution. So now let's take q in t. Well, this thing stopped working, but whatever. So let's take q in t at two different parameters such that all possible powers of them are different. Now, instead of considering the previous set of points x mu, now I'll consider these points x mu, which are determined by certain powers of q in t. Basically, the power of t tracks the number of this coordinate, and the power of q will track the corresponding sizes of parts of my partition mu. So if we consider this set of points and try to do exactly the same manipulations I did for factorial Schur functions, it turns out that the solution still exists, and namely there exists this unique family of symmetric polynomials, which satisfy this condition of the degree, and which will vanish at all these points x mu, unless lambda is contained in mu. And for some reason, it turns out that these symmetric polynomials, if you look at its top homogeneous degree, it somehow will just pop out the Macdonald polynomial, which, so yeah, thankfully, Macdonald polynomials already appeared in the first half of today's lectures, so I will not spend a lot of time reminding about them, but Macdonald polynomials, just as a reminder, is a certain generalization of Schur functions where I add these two parameters q and t, and which are determined by a certain triangularity property, and they are orthogonal with respect to a certain scalar power on symmetric functions, or symmetric polynomials, if you will restrict it carefully. So, and yes, so this solution was found by several, it was found in 3 different works, which appeared more or less in this like very similar time. It basically has appeared first in the works of Sahi and Knop in '96, and then slightly later in the work of Okounkov also at the same year. And well, this is a different solution, and it turns out that, well, I'm not talking about any other solutions, because there were no other solutions. So it turns out that when people have tried to find solutions for this interpolation problem, for some reason, the only solutions they have managed to find somehow naturally involved either Schur functions or Macdonald functions, which is also a certain part of the magic. Because there is no like a priori reason you should expect that this interpolation property should somehow lead to symmetric functions from Macdonald hierarchy. So okay, so this was this progress done in '96. And then when people try to extend these results further, they realize that, well, there are actually no more solutions of this problem if you'll try to consider similar points. So namely, in '97, Okounkov kind of finished all this discussion by proving the following classification. So if you consider all these interpolation problems for points x mu, where the corresponding coordinate of this point depends only the corresponding part of the partition mu, then all the possible interpolation problems satisfying this vanishing property are fully classified by the following 3 examples. So either the example on the first line, which is, I have not talked about it, but it's relatively simple. We'll give so-called factorial monomial functions, which are defined by just taking monomial symmetric functions and replacing powers of x there by these shifted powers of x, similar to how I defined factorial Schur functions. Then there is this example of factorial Schur polynomials, which was my first example. Then there is this generalization of interpolation Macdonald polynomials with, like, not of the type A, but in a certain sense of the type BC, which is determined by these points determined there. And that's it. After these classification results, there were no more solutions to this interpolation problem, at least in the world of symmetric polynomials. There were other results about it. So if people want to ask something about like not symmetric polynomials, but for example, supersymmetric polynomials or Laurent polynomials. So there was some progress after this. There were like some works by Rines or Kornwinder about Laurent interpolation polynomials. There were some works about supersymmetric interpolation polynomials, which has related to so-called q-Sure functions. There were also some non-symmetric analogs of all this story. But more or less, this slide shows all types of problems which, well, all types of solutions to this interpolation problems which were known so far until more or less recently. Yes?
Can you comment on Laurent polynomials? So what symmetric Laurent polynomials do you get?
I mean, no, okay, basically, I should have written Macdonald. Yeah, basically, there is a generalization of this BC Macdonald polynomials, which will be not polynomials, but they will be Laurent polynomials. And then from this generalization, you can generalize it further and further, and then you will get some, I believe it was found by Rines, there is some common generalization with kind of like both generalizes this interpolation BC Macdonald polynomials and also Kornwinder polynomials. And this will be like certain Laurent symmetric functions determined by, again, certain interpolation vanishing property. So yeah, this is work which was mostly done by Rines at some point, and then it was slightly extended by Kornwinder as well. But yeah, so this is the general background about all this interpolation symmetric functions business. So what I'm going to talk about today, so it turns out that when working with a certain integrable model, I have managed to find one more solution to this problem. So namely, for this other solution, what I'm doing, so now let's again take some parameter q and parameters alpha, which I will assume that all the possible ratios of alphas are not integer powers of q. And then I will consider this set of points where now this parameters alpha will still try to kind of track the order of this coordinate, but the powers of q will track not the parts of my partition mu, but instead they track the differences between parts of my partition. So if you, for example, compare with the previous results, so in all previous results, namely for this interpolation Macdonald functions or for factorial Sure functions, all these coordinates solely depended on the corresponding parts of the partition. So now for this new solution, I'm taking points which will depend not on the parts of the, where single coordinates will depend not on the parts of the partition, but instead they will depend on differences of parts of the partition. This is the reason why this example is not covered by that classification of Okouenkov on the previous slide. And then it turns out that if you will take these points and again we'll run all this business with interpolation functions, then again you will have a solution which will satisfy this vanishing, like infinite vanishing property. And well, it was not observed before. And this is the main point of my talk today, talking about this new functions f. Yes?
But could you repeat again why why it didn't fit previous classification? Or?
So yeah, my previous specification does not work because here you see the coordinates. For example, the first coordinate, it depends on the difference between mu1 and mu2. While the previous classification, it only covered the cases when these points, each coordinate depends on a single part of the partition. So the first coordinate depends on mu1, the second coordinate on mu2, and so on and so forth. Well, okay, it doesn't matter because the coordinates are kind of symmetric, but it's still like each individual coordinate depends only on one part of this partition. So okay, and then if you will look at the top homogeneous part of this new functions f lambda, then what you will get, you will actually get Macdonald polynomials with t equal to 0. So in a certain like part of integral probability, such functions are called q-Whittaker functions. So for this reason, I'm calling these new functions interpolation q-Whittaker functions. And well, probably one more remark I should make about this function is that while this top homogeneous part can be obtained from Macdonald polynomials by setting t equal to 0, these whole functions cannot be obtained from interpolation Macdonald polynomials by setting t equal to 0. So you cannot like simply obtain this new set of functions by taking this previous example of interpolation Macdonald polynomials and sending t equal to 0 there, because sending t equal to 0 there will make this interpolation points degenerate, and this will not work. But instead, it will turn out to be some completely new family of functions, which is not directly related to interpolation Macdonald polynomials, but instead is defined and found in a completely different way. So, okay. So that's it for this part. So if there are no questions about this interpolation problems, let me then continue, and let me actually describe how I have found this solution and where the solution comes from. So, well, in general, finding solution to infinitely many linear equations is not a trivial task, and I did not find the solution by just magically guessing this set of right points to find this solution of infinitely many equations. So all the solution and these functions come from a completely different story. Namely, they come from a certain integrable vertex model. So let me explain this integrable vertex model. So to talk about this integrable vertex model, so what I will do, I will first explain what are the states of this model. Then I will explain what are the weights in this model. And then my functions will be determined as a partition function of this model. So now, first of all, let me explain what are possible states of this vertex model. So my possible states will be encoded by path ensembles on a square grid, where this path ensembles always go from, they always come into my model from the left boundary. They are always going in the either right to the right or upwards. And moreover, I have one additional restriction that no path can do two right steps in a row. So whenever my path is doing a right step, it is forced to go up on the next step. So this will kind of make these pictures look somewhat triangular, because my paths are always forced to have like move at least along the diagonal or even above it. And then I will encode my partition lambda, which will be the index of my function. I will denote this partition lambda by the top boundary, by the number of paths at the top boundary, by taking the differences between the paths of partition being the corresponding number of paths exiting the top boundary. So for example, in this picture, this picture will correspond to the partition lambda being 4, 3, 1. Lambda 3 will be equal to 1, lambda 2 will be equal to the sum of 2 and 1, and then lambda 1 will be equal to the sum of all paths at the top boundary. So okay, so this is the possible states of this model. Now, to define the weights of this model, this will be a little bit of a mouthful, so bear with me. So to define the weights, first I will actually explain on which parameters this model will depend. So this model will depend on Q and also 3 families of parameters. So there will be parameters x, which in the end will correspond to the variables of my functions. There will be parameters alpha, which also has figurated in this interpolation property. And then there is also a second family of parameters beta. And then these 3 different families of parameters will be kind of attached to the lines of this grid in the following way. So all the x parameters will be assumed to be attached to the rows of this model. All the beta parameters will be assumed to be attached to the columns of this model. And then the alpha parameters will be a little bit weird. They will be going along zigzag paths going through this model. And after defining all these different parameters and how they attach to the lines of this model, I will be defining weights. So now there are like 2 pictures which you should see here together. So there is this picture of how parameters work. And then there is also this arbitrary path ensemble for which I will be defining this weight. And so for the path ensemble on this grid, I will be defining the weight as the product of some weights sitting on the left boundary and some local weights sitting at each vertex. And at the left boundary, the local weights will look like this. It will be a certain ratio of q-Gamma symbols, which will only depend on the alpha and x parameters corresponding to this edge at the left boundary. And m in this expression is the number of paths entering along this edge. And then For the vertex weight, it will depend on these three parameters, x, beta, and alpha. X is corresponding to the row, but beta corresponds to the column, and alpha corresponds to one of these zigzag paths which crosses this vertex. And well, the weight itself is written here. It's again some combination of cryptographic symbols. It's not so important what it is. Probably the more important thing is that this weight is actually the orthogonality weight of so-called q-Hahn orthogonal polynomials. That's why this whole model and this class of weights is referred to as q-Hahn weights, and that's why I'm using the name q-Hahn for all these models. And well, finally, combining all the pieces of definition together, this function, I can define these functions f lambda, which depend on these x's, alphas, and betas, by looking at all path ensembles which have this prescribed boundary condition on the top, and each path ensemble contributes weight corresponding to the product of all these vertex and boundary weights. So this is a somewhat cumbersome definition. It might be quite complicated if this is the first time you're seeing vertex models, but I hope at least some part of the audience is familiar with this type of definitions.
Sorry, could you go back to the last slide for a second?
Sure.
Does the fact that the which corner of the red path touches make a difference?
So it always, the alpha will always be from the path which comes from the bottom and goes to the right, always. Yeah, I have tried to draw the zigzag path so it's like clear that the corner coming from the like north west is kind of like not actually touching this vertex. This is the reason, like this depiction is exactly for the reason that my weights will only depend on one of these alphas. So okay, so this is the definition of this vertex model. So let me comment about it a little bit. So first of all, if you will forget about these different parameters, alpha, beta, and x, and set all of them to be equal to some numbers, namely if you like set all x's to be equal to s, all alphas to be equal to some number 1, and all betas to some other number t, and assume some inequalities between them, you can show that all these weights will actually be some positive numbers. And you can also show that they will sum to 1. And the model I'm describing is actually just a certain generalization of q-Hahn Tasep or q-Hahn boson model introduced by Povolotsky like 10 years ago.
So in which direction will you have time? Like,
so
what
yes,
does on that picture is time?
So let's go back to this picture. So if you look at this picture and you will think about vertical direction as time and horizontal direction as like some lattice on which my particles live, then each of these paths can be thought of as a trajectory of a particle on this one-dimensional lattice.
So is it moving up?
So yes, if you will look at this behavior of paths, so what will be this model? So this will be trajectories of so-called q-Hahn boson model. At each side of the lattice, I am allowed to have arbitrary many particles. And at each discrete time, I'm taking a side of my lattice, take some random number of particles at this, and move them one step to the right. So this is exactly what's happening on this picture. So on the 0 level, I have no particles. Then in this example, on the next step, I have 2 particles coming from the left boundary. Then on the next step, I will have 1 more particle coming from the left boundary. And then these 2 particles which were at the first spot, they simultaneously move to the next spot. And then on the last line there, it will correspond to 1 more particle entering from the left. Then the next particle, so the particle which was in the first place, move 1 space. Then 1 of the particles which was on the second space remains there, while 1 of them moves 1 more step to the right.
And is there an entrance law? Like, how do they?
So yes, and the weights here, they determine the probabilities of what is actually happening. So the vertex weights determine what is the probability of how many particles I take from one space and move it 1 space to the right. and these boundary weights on the left boundary, they determine the distribution, how many particles are entering at each time moment into this model. Well, strictly speaking, you need to renormalize them. You need to add some infinite Pagammer symbols here to make them sum to 1. But after renormalizing them, this will be probability distributions. They will all sum to 1.
For the boundary weights, you just said little n to infinity, right?
Yes. Well, I mean, removing infinite Pagammer symbols, yes. So yeah, you can see also that these boundary weights can be obtained from the vertex space there by sending n to infinity. This is true. This is like, so these boundary weights are actually not very mysterious. So okay, so this is first generalization of this model. So this model is just a generalization of all these q-Hahn, TASEP, and q-Hahn boson models. Then when instead of saying that all parameters are equal, we only say that alpha and beta parameters are equal between each other. Then this model was studied earlier by Borodin and Wheeler, and they have looked at this model to define a certain spin generalization of q-Whittaker functions. And for this reason, these resulting functions of lambda are called spin q-Whittaker functions. And they have studied this model when all these parameters alpha and beta are equal to each other. In this particular case, this model can be actually obtained through a certain procedure from 6 vertex models. And it can be basically the integrability and properties of this model can be reduced to properties of 6 vertex model. And then, while they have studied these functions of lambda, they have showed that they indeed generalize q-Whittaker functions and so forth and so on. And also, there is also another example where this model has appeared earlier. So if you will take, again, this parameters alpha and beta, you will set all parameters beta equal to each other, all parameters alpha equal to each other, with the exception of one of these parameters alpha, which we will set to 0. Then this model also has appeared earlier in the literature. It was studied by Matteo and Leo in like 2020s. And well, they have determined, they have used their model to determine an alternative version of spin q-Whittaker functions, which, well, as it turns out, are all particular cases of these general functions depending on all these alphas and betas I have defined on the previous slide. So okay, so this is the earlier examples of this model. Now let me talk about properties of these functions. So first of all, if you will look at these definitions, there are a lot of them, but probably it should not be obvious from these definitions why, for example, whatever I have obtained as this partition function should be, for example, symmetric in variables x. Because, for example, on the first line, which corresponds to x1, I will always have only one corner of my path ensembles, while on the top line, these path ensembles can be like everywhere. So it should not be obvious that this resulting partition function will be symmetric in x's, but it turns out to be the case. So this is a certain thing I will be talking about more probably in the last part of the talk. But it turns out that the model which I have defined in terms of all these parameters, alpha, beta, and x, it turns out to be so-called integrable, where for my purposes, by integrable, I mean that there are certain families of Yang-Baxter equations which can be found inside this model. Again, I will not talk about it right now. I will talk a little bit about it in the end of my talk. But using this integrability and Yang-Baxter equations, we can basically do a certain argument which exchanges rows, and it will show that this resulting partition functions will turn out to be symmetric in this variable x's. And moreover, using this Yang-Baxter equations integrability, we can show that in addition to the fact that this is symmetric polynomials, these functions will also satisfy a certain version of Cauchy identity. Namely, if you will take this sum of these products of functions in two different sets of variables, where one functions will be corresponding to parameters alpha and beta, and the other functions will correspond to parameters alpha and beta, but swapped between each other, then this sum will very nicely collapse into product of infinite Pagammer symbols. And for example, you can observe that when you set parameters alpha equal to 0 and beta going to infinity, this right-hand side will exactly be the Macdonald Cauchy kernel for t equal to 0. So it's consistent with this observation. And it turns out, well, if you haven't seen Cauchy identities earlier, basically what this means, it's how one way to interpret this identity is that in a certain sense, these functions, the spin cubical functions f lambda, they're kind of, well, they're not orthogonal because you need to solve these parameters alpha and beta, but they're kind of dual to each other after swapping alpha and beta parameters. So these are these two properties you can prove using integrability. And also there are a bunch of other properties you can prove. So first, for example, you can show that when you set all the parameters beta equal to 0, then these functions will turn out to be polynomials of degree lambda, no greater than lambda. And also you can show that as promised by these interpolation properties I have described earlier, these functions have constructed indeed will vanish at these points alpha to corresponding powers of q. And then, well, combining these two properties together, it will imply that these functions I have constructed are indeed this interpolation q-Whittaker functions which solve the interpolation problem for these points x mu.
What do you mean when you say that only at 0 there's a solution to the interpolation problem? It seems that your vanishing property is for all.
Yes, so the vanishing, so yes, the idea here is that interpolation property, it first of all restricts the degree of the polynomial because it needs to restrict like the amount of freedom and coefficients. And also it determines like a bunch of linear equations which are the values of these polynomials. So it turns out that the linear equations will hold for these functions for any beta, but the degree condition will hold only when beta is equal to 0. And that's why my solution, it's like the solution for the interpolation problem is only depends on one first set of these parameters, because if you will consider this general beta, then the degree will not quite be the right
Still
one.
are going to be polynomials, just of
They will be polynomials, but their degree will be very random. It will be a
particular understanding what the degree is?
well, it's not like a particular understanding. So the picture here is that, how to explain it? So what you can do, you can try to ask yourself if these functions have some stability properties. For example, what will happen if you like take one of these xn's and set it to 0, or for example to alpha n. And it turns out, I'm not writing it down here, but there is certain stability property for these functions. And if you will try to define, using this stability property, this symmetric functions in infinitely many variables, what it will turn out that when beta is equal to 0, this infinitely many variables will still give you some nice symmetric functions with bounded degree. But if you try to make this number of variables infinite for arbitrary beta, the right object you will need to be looking at is not actually a symmetric function, but it's more something like a completion of the algebra of symmetric functions in infinitely many variables. It will have like unbounded degrees and so on and so forth. So the right way to think about it is that while for finite number of variables it will be always a polynomials in X, in reality you should probably think about it as like some rational functions in X's, because when you will try to like make the number of variables infinite, it will basically require you to have arbitrary large degree. But yes, so that's basically the main results about the functions we have here. So probably for the last, I believe, 10 minutes I have here, let me speak a little bit about where all these results come from. So first of all, the results on this slide are actually simple combinatorics. So basically, for the results on this slide about the degree and vanishing, you just need to look at the vertex weights carefully when beta is equal to 0 and see that like the weights themselves will have nice degrees which will sum up to something no greater than the number of boxes in lambda. The vanishing property also follows directly from the model. You can just look at the left boundary weights. You can see that if in this left boundary weights you set x equal to alpha times q to some power, then this expression will vanish for large enough m's, because it will always have like a term which will be forced to be vanishing if x is plugged to be equal to alpha times some power of q. And then from this vanishing, you will see that plugging these points x mu basically restricts you to configurations of on the square grid, where on the left boundary you have not arbitrary number of paths entering, but instead on the first row you are bounded by at most mu1 minus mu2 paths. On the second row you are bounded by mu2 minus mu3 paths, and so on and so forth. And then by some elementary conservation laws you can show that this condition is equivalent to saying that lambda is strictly contained in mu. For example, from this picture you can see that lambda 1 is like, if there is such a configuration, lambda 1 must be less or equal than mu1, because lambda 1 is sum of numbers on the top, mu1 is sum of the bounds on the left, and well, if I have lambda 1 paths in this model, I should have at least lambda 1 paths entering this model, so it should be less or equal than mu1. And similarly, you can do it for mu2, mu3, and so on and so forth. So this results are simple combinatorics. The complicated results here are actually trying to explain why this model with parameters alpha, beta, and x, why this model is actually integrable, and why it has Yang-Baxter equations, and in particular why the resulting functions are symmetric. So to explain it, what I will do, I will make a certain detour in the world of quantum loop algebras. So it turns out that the integrability of the model is most naturally seen if you will try to look at the representations of quantum loop SL2 algebra. So namely, well, probably I should not expect everyone in the audience to be familiar with these representations. So let me try at least give a rough outline of what representation theory of this loop algebra looks like. So first of all, remember that we have the algebra SL2, and you have for this algebra SL2, you have highest weight Fermat modules, which I will denote here Vs, where S is the highest weight. So then what you can do, there is a certain very nice choice of deformation of the universal enveloping algebra of SL2, which adds this quantum parameter Q to it. For my purposes, I will always assume that this Q is a generic parameter. I'm not talking about any cases when Q is the root of unity or something like this. So in the case when Q is a generic parameter, this very special deformation of SL2 algebra, which is denoted by UQSL2, it will actually have a very similar representation theory for the original SL2. It will turn out that it is still, its representations are basically all Riemann modules with certain highest weight. And well, if you want some connection between classical case and this quantum case, usually the highest weight in the quantum world corresponds to Q to the power of the classical weight. That's at least how I will treat it. And then, so the representation theory and the retrievable representations, when you do this quantization, remain the same for generic parameter Q. But what changes and what becomes non-trivial is the structure of tensor products between representation becomes very non-trivial when you do this quantum deformation, because one of the main features of this quantum deformation is that your algebra becomes so-called non-co-commutative. Namely, if you will take two representations of this quantum SL2 algebras and take tensor products in different orders, then there is still some natural way to define the action of your quantum algebra on these tensor products. But these actions will not commute through this naive change of factors in this tensor product. And instead, if you want to get some maps between tensor products in different orders, what you need to do, you need to look at so-called R matrices, which try to intertwine between these two different ways of tensoring two representations. And for generic representations V and W, in this case, there will be some isomorphism between these two tensor models, which will be called the R matrix corresponding to this pair of representations. So this is the story about UQSL2. Now I want not just UQSL2, I want loop algebra UQSL2. So for the loop algebras, what are loop algebras? Well, in the classical case, they correspond to taking your usual algebra and then considering Laurent polynomials and some additional variable t. This is called loop algebra or loop parameter. And what are representations of this loop algebra? So for this representation theory of loop algebras, it's actually way more complicated than representations of non-affine algebras. But I will not talk about all representations, but in particular among the representations of these loop algebras, you can find the representations V lambda Z, where V lambda is the Fermat model for the classical SL2, and Z is this affine parameter, which corresponds to basically just saying that some polynomial in T will act by setting T equal to this affine parameter Z. So these are called so-called evaluation models, and basically using this procedure, you can lift any Fermat model for the classical algebra to a certain model for this loop algebra, which will now depend on these two parameters. One will be the highest weight, and the other one will be the value of this variable t. And now finally, you can combine all of this together. You can construct so-called quantum loop algebras. I will not define this to any extent. The only thing I care about is that these quantum loop algebras also have these natural representations which depend on these two parameters, which is the highest weight and the affine parameter. And these will be the representations I need for my construction. So to be somewhat short, so the main result which is relevant for my model is the following idea. So if I will reparameterize this 2 degrees of freedom for my representation, namely if I will say that my highest weight is the ratio of some numbers b and a, and my spectral parameter or affine parameter is the product of these numbers, then it turns out that I can draw this commutative square of a bunch of isomorphisms between different tensor products of these representations. And the main result here, so there is the R matrix which just swaps these tensor factors. But also in addition to this, there are these half R matrices which only swaps parameters A or parameters B. And if you will look at the matrix coefficients of these half R matrices, they will be exactly these q-Hahn weights I had in my model earlier. And the bottom line here is that all this model and all these weird parameters, alpha, beta, and x, some of which were like along the zigzag path, all this is actually coming from just looking at these representations and trying to look what will happen if we will try to just take this matrix coefficient and combine them in some natural way. So namely, what happens here is one vertex of that model, the way how you should interpret this is that at each edge you have some representation living there. The two parameters which we lift on this edge correspond to these two parameters of representations. And then I'm applying one of these half R matrices where I'm swapping only one family of parameters and preserve the rest. And then what you will get is that, well, the family of these parameters will correspond to this row and column parameters which behave normally. But the parameters which you do not switch, they will kind of bounce in this vertex, and they will form this zigzag path going along it. And then using this picture, you can basically interpret all this model I had for q-Hahn polynomials as certain just rule for taking matrix coefficients of this isomorphism between tensor products. And this will imply integrability. And probably for the last slide, for example, to be more precise, this functions f lambda using this interpretation can be written as just a certain matrix coefficient of pretty huge tensor products. You like take tensor products which will depend on what's happening on the left boundary. You take tensor products of what will happen like on the top boundary, and then you will like take the vectors on the left and on the right which will kind of encode the boundary conditions, and then this whole function, so this whole partition function can basically just be interpreted as a certain matrix coefficient, and all this integrability property, all this symmetry and stuff like that, all of this just follows from certain applications of Schur lemmas when you have several like isomorphisms between irreducible representations and they must be equal to each other. And in particular, by looking at isomorphism between triple tensor products, you can get a bunch of Yang-Baxter equations for this model. And then using all of them, you can show that it is integrable and all the results for my functions will actually hold. So, okay. So I guess that's it for my talk now.